So let's go ahead and look at what affects the entropy change of a system then. We'll look at four things: the number of particles, the volume of the system, the phases of the particles, and heat. First up, and the simplest, is number of particles. Again, keeping in mind that entropy is kind of like disorder or messiness, the bottom line is that the more particles you have in the system, the greater its entropy will be. And the reason for this is because entropy is basically a statistics game. The more particles you have, the less chance you have of them being ordered, and the greater the chance they will be disordered. And so for an example of this, let's consider the simple coin toss. One simple way to demonstrate how entropy is determined by the number of particles is the simple coin flip. Here we have 1 penny, and of course you have good old Abe on the front side, and on the back side we have his Lincoln Memorial. And so if we flip this penny, as you know, we'd have a 1 in 2 chance of getting heads again when we flipped it. Now let's suppose that we found a second penny, is our lucky day, and so now we have 2 pennies, and we're going to flip both of them. Suppose I really like heads, and so I want to know what the probability of getting heads is. And as you probably know from probability and statistics, that probability of getting both heads is simply the probability of getting 1 head raised to however many coins we have. So that'd be 1/2 to the 2nd power, which tells me that I should have to flip these coins 4 times before I get heads again. So let me try it out right now. Let me see. Let me flip them and see how many heads I get. Okay, looks like luck was not a lady tonight. I got 2 tails. 2 tails. That was a 1 in 4 chance of that as well, but no heads. Right? So let's keep on going here. Now let's imagine we have 3 pennies. And so the odds of flipping all 3 of these and getting all heads would be 1/2 raised to the 3rd power, or 1 in 8. So I should have a 1 in 8 chance of getting all heads. Let's not stop there though. Let's go ahead and keep on going, and let's do a dozen coins. And so now that'd be 1/2 raised to the 12th power, which is a 1 in 4,096 chance. So I should have to flip all 12 of these pennies 4,096 times before I get all heads again. So as you can see, just a very small increase in the number of particles has a drastic change in probability. You can think of flipping heads as keeping the particles organized. And so to tie this back into entropy and chemistry, as we increase the number of particles, the odds of those particles remaining organized gets very, very, very small, very, very, very quickly. Just to keep on going here for fun, imagine I had 100 pennies, and if I wanted to flip all 100 and get all heads, I'd have a 1 in 1.27 times 10 to the 30th chance of getting all heads there. Crazy. That ain't going to happen anytime soon. And of course in chemistry we usually deal with much, much larger numbers. So just for kicks, let's imagine we have a mole of pennies. Never mind how much money that'd be, or the fact that it would cover the earth to quite a depth and we wouldn't be able to survive. But if we had a mole of pennies, that'd be 6.02 times 10 to the 23rd. And the probability of getting all heads if we were to flip an entire mole of pennies would be 1 over error. My calculator can't compute. Your calculator can't compute. That is a huge, huge number there. So as you can see, the odds of having a mole of particles, which is relatively small in most circumstances, at least in chemistry speak, the odds of having a mole of particles organized is vanishingly, vanishingly small. And so as we increase the number of particles, our entropy increases very, very quickly because it's just too hard to keep up. Alright, as another example, let's think of helium gas. Which has more entropy? 1 mole of helium gas in a 1 liter container at 25 degrees Celsius, or 1/10 of a mole of helium gas in a 1 liter container at 25 degrees Celsius? Well, again, it's an entropy game. It's a statistics game. If you have 1 mole, you got 6 times 10 to the 23rd particles. all these particles are spread throughout the container because the gas fills its container, as you know. On the other hand, if you have a tenth of a mole, you only have a tenth as many particles. And so correspondingly, that would be about 1 dot. So as you can imagine, it would be very, very difficult for all 6 times 10 to the 23rd particles to, for example, move into this one little corner of the container. You're not going to see that happen. However, if you have, say, a tenth as much, the odds are greater, still very, very small, but the odds are greater that they could all fit in this very, very tiny space. And so the fewer particles you have, the greater the chance of being ordered and neater and more condensed. The more particles you have, however, the greater the chance they will be disordered and not neat and more spread out. And so this has a greater entropy because it has more particles. The second thing to consider with entropy is volume. Basically, the greater the system's volume, the greater its entropy will be. Again, that's because it's a statistics game. The more space particles have, the more likely they'll be spread out, and therefore less ordered, and have greater entropy. So again, we can consider this time 1 mole of helium gas in both cases, but now the difference is the size of the container. Originally we're going to have 1 liter, and over here we're going to have 10 liters. And so if you have 6 times 10 to the 23rd particles of HE in a small container, those guys are relatively condensed and fairly ordered. However, if you move them to a container 10 times its size, those particles are going to spread out, be more dispersed, more disordered, and your entropy will be greater. And so the greater volume has a greater entropy, a greater S, and your smaller volume has a lesser entropy, or smaller entropy. The third thing to consider is phases, and this is really important actually. Solids generally have less entropy than liquids, which have less entropy than gases, and gases are like an anarchist dream. The reason being is that, as you recall from earlier in the year, particles in solids are practically locked into place. Consider, for example, our good old crystal of salt, sodium chloride. This is about as ordered as you can get, with alternating patterns of positive and negative ions. These guys are jiggling, but that's about it. No movement for them, they're on lockdown. And so the entropy for salt is very, 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 very low. If you look at a liquid, however, although these guys are fairly close together, they are mobile, that is, they are free to move around. This extra mobility means that they are more disordered and more random, and so they have more entropy than what a solid does. And lastly, you have gases. Gases are like free-range particles. They're just whizzing and flying and jiggling all over the place. There's no predicting where they're going to be. Imagine looking at our ideal gas law simulator again. Those particles are literally bouncing off the walls, and so they have a lot of entropy. And so if you compare entropy of the 3 phases for water, gassy water would fill its container. Liquid water would be all condensed at the bottom. And solid water would actually take up slightly more volume, but it too is all in one spot, basically. The main thing, though, for these guys is mobility. Liquid water, again, is free to move. The solids can only jiggle in place, and so the solids have very low entropy. The liquids, because they're more mobile, has more entropy. However, even their mobility cannot compare to gases, which are crazy with entropy. They have the most entropy of all 3 phases. So remember that. The last factor that affects entropy is heat. And here, the higher your temperature, the more entropy you'll have. The reason being because, as you know, the more temperature you have, the faster the particles will move, the more they jiggle. The more motion means the more randomness, and the more chance they will be disorganized and spread out. So as you heat a substance, its entropy will increase. So here we have 1 mole of helium, in the same size container, 1 liter. Now, however, we have different temperatures, one at 25, one at 125. And so even though we have the same number of particles, and even though they might initially be in the same locations, the one at 25 degrees Celsius, although moving quickly, is not moving as fast as the ones that are hotter. And so the hotter sample has a greater entropy change, greater entropy. So let's go and take a look at a few more examples, and as we click through them, pause the video for a moment and make a mental prediction, or on paper, of whether it will be a positive entropy change, whether entropy will increase and become more disordered, more spread out, or if it will be a negative entropy change, things will become neater or more condensed. So take a moment to think about water evaporating, going from liquid to gas. Okay. Hopefully you chose a positive entropy change for this process. The reason being because we're going from liquids, which have a relatively low entropy, to gases, which are going crazy with entropy. And so here we're going to have a positive entropy change as the water gets more and more disordered and more spread out too. Next up is the synthesis of ammonia from nitrogen and hydrogen into NH3. So take a moment to predict. Hopefully you chose a negative change in entropy. Here, you'll notice they all have the same phases. They're all gases, and so we can't use that trick now. And so next we'll rely on the next most important factor in entropy, and that is the number of particles. Looking at our balanced equation, we have 1 particle of nitrogen combining with 3 particles of hydrogen, and that combined to make 2 particles of NH3. So 1 plus 3 equals 2. So we're going into fewer particles. Fewer particles means there's less chance to be spread out or disordered, and so entropy will decrease. Next up is calcium carbonate decomposing. Take a moment. Hopefully you chose a positive entropy change. As you recall, decomposition is the opposite of synthesis, so it should come as no surprise that it has the opposite sign as a synthesis reaction. We are, after all, making more particles. 1 particle is going into 2 particles. Not only that, but take a look at this. We're also making a gas here. We're going from a very neat and ordered solid in chalk, calcium carbonate, to another neat and ordered solid, calcium oxide, to a crazy gas. And that gas will have a much larger volume, and therefore a much larger entropy than the chalk that you started out with. Some more examples. Let's look at water freezing. Take a moment, take a guess, and hopefully you chose negative. This is pretty much the opposite of the evaporation scenario. We're going from a liquid, but this time we're going into something that's more ordered, a solid, and so that is a negative change in entropy. Next up, the synthesis of salt. And hopefully you decide it is positive. Whoops, just kidding. Negative. Again, look at particles. We have 1.5 particles going into a single particle, so that's enough to have a decrease in entropy. But, get a load of this. We have a gas here as a reactant. We ain't got no gas on the product side. We have lost a gas. This is the opposite of the chalk consideration. We are losing a gas, and so this gas, which was once free as a bird, is now stuck in the solid phase with sodium ions, and so its entropy has decreased significantly. Once we make this salt, let's go ahead and dissolve it. What's it going to do? Why, that would be a positive change in entropy. You can look at particles. You got 1 particle going into 2 particles. That's enough for a positive change in entropy. But wait, there's more. Take a look at the phases again. We start off with a solid, which you know is very neat and orderly, has a very low entropy. And then it's going into aqueous. We haven't talked about aqueous solutions yet, but at least not in entropy. But as you recall, that means that your ions are spread out in water, dissolved by water molecules, and because of that, they are mobile. They are free to move around. And so aqueous things tend to have a higher entropy because they are mobile now. And lastly, let's look at the expansion of a gas of nitrogen from a volume of 23 liters into 100 liters. And that is a positive entropy change. Again, it's a statistics thing. Something in a very small volume is going into a larger volume. It's spreading out, has a greater chance to be disordered. And so that is a positive entropy change there. So that's how you can make some qualitative predictions about reactions. But you can also calculate the entropy changes of a reaction as well. And to do that, we're going to look at something called standard entropies. Again, you might remember the degree sign from the enthalpies of formation, delta HF. We're going to see it again with entropy now. We need something to base it off of. For example, if you measure the height of a mountain, you usually base it on sea level. And so our sea level for entropy is a perfect crystal at absolute zero. As you recall, solids have the lowest entropy, and a perfect crystal would have the lowest entropy of all. Also, you'll remember that colder things have less entropy, and so if you go as cold as you can get, you're going to have the least amount of entropy possible. So we're going to cool it all the way down to absolute zero. The heck that it's impossible, we're going to do it anyway. And so if we could have a perfect crystal at absolute zero, it would have zero entropy. S naught equals zero. That, of course, is impossible. You can't have a perfect crystal, and we can't get to absolute zero, so we're never going to have anything with zero entropy. But it's still fun to imagine, and so that's what we're going to do. Here are some sample standard entropies you might find in the back of your book in your appendix. Things to note. How do the standard entropy values of solids, liquids, and gases compare? Well, we have gases here in the form of hydrogen and water vapor, and they're 131 and 189 joules per Kelvin. That probably doesn't mean a whole lot, but if you compare that to liquids, liquids have significantly less entropy, about half as much in fact. Liquid water, for example, only has 70. And solids have even less. Now granted, this is a pretty darn near perfect solid and diamond, but still a very, very, very low entropy of only 2. So again, solids have low entropies, liquids are somewhere in the middle, and gases have the most. It's also worth comparing hydrogen to water. Hydrogen has a little less entropy even though they're both gases. The reason for that is because water is it's a more complicated molecule. It's got more bonds, it's got more ways to rotate, more bond angles to squeeze, and so these complicating factors will increase your entropy. And lastly, does your standard entropy equal zero for pure elements as the heats of formation did? Well, take a look. We got hydrogen here. That's a pure element. We can assume standard conditions, and no, that is not a zero. Elements do not have entropies of zero. They do have an entropy. The only thing that can have zero entropy would be a perfect crystal at absolute zero, and that's not the case for our pure elements. So to calculate the entropy change of reaction is really quite simple and should look really familiar. All you do is you add up all the entropies of the products and add up all the entropies of the reactants, subtract products minus reactants, and that will get you the change in entropy of your reaction, just like it did for heats of formation back in the day. The only trick is to remember to multiply by coefficients from your balanced equation. So let's go ahead and take it for a spin in our first and only example of this, and that will be to look at the entropy change of the decomposition of sulfur trioxide into sulfur dioxide and oxygen gas. Don't try this at home. Both these gases are noxious. They will poison you as they make acid inside your lungs as you breathe them in and they dissolve in water. So let's first go ahead and make a prediction of the sign, and I'll let you do that for a moment. Hopefully you predict a positive entropy change because, well, they all have the same phases. No big deal there, but we're changing the number of particles. We got 2 reactants going into 3 products, and so we are increasing the number of particles, so we're increasing the disorder or randomness of our system here. So let's go ahead and calculate it. I know many of you have different ways of doing this. Go ahead and do that now, and I'll put up mine and we'll see how we compare. Okay, did you get an entropy change of positive 187 joules per Kelvin? I hope so. I hope I did it right. Well, that brings us to a conclusion of our first lesson in thermodynamics. Again, as a recap, we talked about the difference between spontaneous and non-spontaneous processes. A spontaneous process is anything that just happens in nature by itself. You don't need to force it, coax it, or push it into happening. It will occur by itself. Then we looked at how we can predict or tell if a process is spontaneous. And the test that we have so far is entropy. Does the entropy of the universe increase during this process? If the answer is yes, the entropy of the universe does increase, then yes, this process is spontaneous. If the entropy of the universe does not increase, then no, the process is not spontaneous. In the next video, we'll have another test to determine the spontaneity of a reaction, and that's something called Gibbs free energy. But until then, I'll see you later.